Hello everyone, my name is Samuel from Universidad del Istmo in Oaxaca, and I'm here today to expose our research about relationship between microhardness and hydrogen diffusivity in a tempered experimental vanadium molybdenum steel project was carried out at the facilities of the Instituto Tecnológico de Morelia in Michoacán at the Universidad del Istmo in Oaxaca. Here I present a complete image of the poster and then I will continue with the explanation of each part. Therefore, my presentation consists of the following parts: introduction, general objective, methodology, results, conclusions, acknowledgement, and the main reference. Firstly, as an introduction, it can be mentioned that steel is one of the main structural materials. For example, its importance is relevant in the construction industry, the automotive industry, as well as in the petrochemical industry. Tempered martensitic steel has high hardness, toughness, and fatigue resistance due to the application of heat treatment. It has been widely used in industries that require high-strength steels. However, atomic hydrogen can be trapped inside a tempered martensitic steel by a number of defects, which lead to the reduction of mechanical strength due to the hydrogen embrittlement phenomenon. Hydrogen entrapment has been studied in some advanced high-strength steel such as dual-phase steel using hydrogen permeability technique. The general objective of the work was to determine the effect of the microstructure on the diffusivity of hydrogen in an experimental steel. For that, a commercial Ag4140 steel was melted to modify its chemical composition by adding a ferroalloy of vanadium and chromium to adjust the chemical composition to 0.3% vanadium. The steel was then conditioned, explained in this section of the methodology. The annealed steel was austenitized at a temperature of 1000 Celsius for 40 minutes and quenched in oil with stearin to obtain a martensitic microstructure. Subsequently, the tempering was carried out at two different temperatures, 530 and 580 Celsius with 15 minutes of elapsed time. In addition, the tempering temperature of 286 Celsius was tested with 15 minutes of elapsed time to compare the behavior of the two tempering states. At a tempering temperature of 530 Celsius, two more tempering times were tested, 120 and 360 minutes. The purpose of the selection of this temperature and time was to promote the formation of alu-carbide. The electrochemical hydrogen permeability tests were performed by means of the double hydrogen permeability cell standardized by the Van Natten and Tarczewski. The experimental configuration consists of a charged cell with a 0.5 molar sulfuric acid solution with 0.2 grams of arsenic nitride to prevent hydrogen recombination, and an oxidation cell with a solution of sodium hydroxide 0.1 molar, as shown in this figure. Well, as a fourth point, the results obtained are present. We have the chemical composition of experimental steel with a 0.38% in carbon, 0.2 of molybdenum, and 0.3 of vanadium approximately. We can observe the microstructure of the steel in the received condition and the martensitic microstructure that is obtained after quenching. Also, we have the micrograph of the membranes that were tempered at different times with a temperature of 530 Celsius. Here we can observe that cracks appeared on this microstructure, which is very curious because the effect has not been reported in temperate stills. On the membranes tempered at different temperatures with a time of 15 minutes, cracks were also observed except in one of these. Hydrogen has different permeation rates due to the different traps present in the microstructure, grain boundaries, or precipitate of alloy carbide. In the first figure, figure 15, it is observed that the longer the tempering time, the more time is needed to reach the steady state. On the other hand, in the following figure, figure 16, it is observed that at a temperature of 530 degrees, there is a rapid saturation of hydrogen in the sample. With respect to the microhardness and the diffusivity of hydrogen, an almost inverse behavior is observed with respect to the ballast. This means that there is the presence of traps that prevent the diffusion of hydrogen, which in turn generates hardening of the material. This phenomenon can be verified with the graph that relates the microhardness with the density of traps which have an almost identical behavior, evidencing the presence of hydrogen traps as well as a secondary hardening phenomenon caused by the alloy carbide that precipitate in the four tempering states. In conclusion, we can say that the hydrogen diffusivity can be decreased by increasing the tempering temperature or by increasing the tempering time. Before, the diffusivity decrease and increase occur first. This is related to the amount of hydrogen trapped. A greater amount of hydrogen trapped is related to a lower diffusivity and greater microhardness. The decrease in diffusivity is related to the formation of alloy carbide, and this in turn have a softening resistance or secondary hardening effect. And finally, here are the main references. And thank you very much for your attention.